All right. So today I will go over a few examples of just what the problems or the types of problems that we're going to be solving in class look like, and why do we need numerical methods to solve them. And then we will start our review of linear algebra. So some of that review will be by hand. Your first homework will sort of introduce MATLAB gently, but basically you will learn how to type things in that are related to linear algebra in your MATLAB. So, but in class we will start using it mostly with the lecture 2, which is basically on MATLAB fundamentals. So for another week. Okay. Now, if you want to prepare, go online. Like I already in my lecture 1, there's like where to go, basically to download MATLAB. Everybody has free access to MATLAB because you're part of UT and UT has a subscription. So it's a site-wide subscription. You don't have to purchase it. You just install it on the machine that you will be using. And if you want to use the labs here on the 3rd floor, it's already installed for you. I will be bringing, or rather Mingu will be bringing a cart with computers. So those computers have MATLAB on, so if you don't want to carry your laptop everywhere with you, you can check out the laptop for use in class here. But those laptops are a little older and cranky. Okay? They're okay, but they might be a little slower than your own computer. Or you might not like switching because then you have to, whatever you work on class, you have to kind of email to yourself or otherwise save that work so you can use it later. Okay. Any other questions? So again, see what's easiest for you. I guess it depends whether you like carrying your laptop around all day or not. Yeah. All right. So let's get going with some examples. Okay. So here's an example of, for first example is what we are not going to use MATLAB for, but it introduces roots as something, or finding roots of an equation as something that you've done before. So everybody knows quadratic equation. Okay? So basically I have a polynomial of 2nd order, and I'm looking for x such that polynomial is equal to 0. That is kind of an abstract form, but a lot of problems we can actually formulate that way. So we have to do our numerical methods for sort of abstract problems so that we can fit different physical problems into those. And I will give you an example of such a problem in a moment. So if I tell you find the root of the following equation, you're going to tell me that those roots are minus b plus minus square root of b squared minus 4ac divided by 2a, right? If I have ax squared plus bx plus c is equal to 0. Right? So if nothing, you know that the formula exists. And you're going to look it up, and you're going to find x1 and x2. Those are great problems where a formula exists, and for those you need a calculator, really. You don't need the program to find the solution. So, great. This one we can solve with everything else that you have already learned. So that this formula has an exact method. So again, A, B, C really refer to these coefficients next to x squared, x, and 1. Okay? Cool. So the results are 1 and 3. Now, if I had, so here's one physical equation. If I had ideal gas law, okay, and I have given pressure P and temperature T, and R in this case is my gas constant, okay, then I can find volume of my gas based on this law. So if you give me pressure and temperature, I can actually, this one is even simpler. I can express volume simply as R times T divided by P. Well, that's ideal gas. Do gases in our reservoirs, are they really ideal? Far from it. Okay? So they're complex gases, so we will actually need a different relationship. And this relationship might not be in such a simple form. Actually, one of those is given as follows. Okay? So this is Peg-Robinson formula. I think, yes. So basically that one is given as pressure is equal to RT divided by VI minus B minus A over VI squared plus 2B VI minus B squared. Okay? And A and B are constants. These are thermodynamic constants that I can find from my tabulated measured results. Okay? So this is a critical temperature and pressure at the critical point, and you still have gas constant in there. So for the particular question, if I'm wondering about methane, which is a common gas in a reservoir, at 50 bars and temperature of 473 K, then A and B are given here. So even if I plug A and B into this equation, for given pressure and temperature, finding VI that solves it is not easy. Right? I can't easily express VI equals 2. The best I can do is I can say, well, P minus this expression equals to 0, and that gives me some function of VI is equal to 0. And that function is a little ugly, which is a colloquial term for nonlinear, okay, or non-polynomial. Okay. So essentially, I will find this as a f of v, express it basically as this 50 is my 50 bar, minus this expression is equal to 0. Okay? And for this class of problems in general, regardless of what this function is, okay, what the function is depends on my physical application, just like here, we will actually figure out how to find numerical solutions to these. So we will basically typically iterate. I'm going to start with a good guess, and then I'm going to improve upon that guess as we go further. And I will figure out when to stop, when is it good enough. We will never get an exact solution, okay? But we will get close enough. And that will be a numerical solution to this equation, okay? So what would you start from? Let's say that you don't know any way to solve this. How would you even start figuring out how to guess a solution?
Assume an ideal gas.
And see how that value does. Okay? So that's a good starting point. So in every numerical method later on, you will often need a starting point and some sort of analytical expression for something ideal, you know, or for something simple is a good starting point. It's still gas, okay? So it should be relatively close. So that's a good starting point. And then how do I evaluate how close it is? So I find VI based on the ideal gas. So I plug it in here and I can, for instance, see how close to 0 it is. And then try some values around it. Or maybe even plot what my f of v is, for v is in some sort of range around that value. And just look at that plot and see how close can I get to the 0. Okay? So those are going to be graphical solutions, but they're a good guess. So let's see. So basically VI is actually, in this particular case, 786.5. Okay? So if you actually put 786 in there, you're going to get 1.87. Then I just try a value. Let's say that I only have calculator and it's not a graphing calculator. Then if I try 750, oops, I went under 0. So I'm possibly somewhere in between. So in between these two values, I start trying to get closer. So I think this is halfway through. It's 0.75. Okay. Then I'm going to go in between these two values, right? So 759 is between 750 and 768. Okay. I'm getting closer, right? And then 754.5. Let's say that this is good enough. Okay. The point I'm making is I also have to decide what is good enough and what is close enough. So let's say that for now we decide this is close enough. So this is going to be my approximation of the V that zeros out this formula. Okay? So our numerical solutions will often actually be close to what I would kind of do if I was just trying out and trying to do smart guesses. It's just that I can employ a computer to search over much more values, okay, so I can be smarter. So it's going to be my extended arm in this search. Okay, so basically if I had a graphing calculator or a plot, I would also like just plot things between 500 and 1,000 and see where it is that I cross a zero. Okay. Okay. So second example would be differentiation. Again, if I had a simple formula y, this can be viewed y of x as x squared minus 4x plus 3. This being a polynomial, if I ask you for dy dx at x is equal to 1, you're going to tell me it is what? Negative 2. So it's going to be 2x minus 4, right? And I'm going to plug in 1 into that. Again, I have a formula. So for cases where I have a formula, I don't need a numerical solution. I will often use those cases to verify that my numerical solution is working well. Okay? So what my derivative is, it's if I was actually looking to design my numerical method, my derivative is a slope of the line that is tangent to a curve, right? So if I was plotting things, so this is just the solution, this is negative 2. So if I have a function, okay, I could plot it. Okay? So at 1, I basically can find the slope to this. Okay? So now I'm looking to approximate that slope in some general case. Okay? If I have a line, how am I going to approximate the slope to a line? Yeah, what's the formula for that slope? What do you need for that line to define it? You need 2 points, okay? And then if you have a point 1, x1, y1, and point 2, x1, 2, y2, what is the slope? Divided by, everybody remembers that? Okay. So that can actually inform my choice of a numerical method, except that I can employ a computer to actually kind of make choice of these points x1, y1, and x2, y2 closer and closer and closer and closer to the point that I want. Okay? And then I can stop very close. So as I'm kind of zooming into that point, I should get really close to what real derivative is. Because that's the definition of derivative. It's limit as delta x goes to 0. Remember that formula in calculus? Okay? So basically my numerical method will be of engaging my computer to get actual values of delta x smaller and smaller and smaller and smaller until I decide to stop and get me that numerical value of the derivative. And I can do it for any functions. It doesn't really have to be this polynomial where I actually have an analytical differentiation. So basically this is a slope. Right? So I know 2 points here, and knowing those points, I can basically make this triangle smaller and smaller and smaller and closer to the value of x I want to find out. Okay? And finally, one example that I'm going to motivate this class with is integration. This would be sort of numerical calculus, numerical differentiation, and numerical integration. Again, in this simple case, if I wanted to evaluate this integral, it would be 1. Can you quickly take a minute? Find the integral. Thirds. I don't know, remember, let me check. Yeah. Again, I have a formula that I integrate between 0 and 1, and you should get 4/3 as a result. So I trust all of you, if you have a moment with a piece of paper, you can do that. Now this is great because I have a formula where I have an analytical way to integrate. That might not always the case. The function that I'm integrating might be very complicated, or it could actually be data. Okay? So all I have with the data when I'm measuring things down the hole, I have depth, measurement, depth, measurement, depth, measurement. My measurement is a function f of depth. But all I have is the values of that function every 1 foot. Okay? So what if I want to integrate that? I don't have a formula. I can't even write that down. I have a table of values. In that case, I need numerical methods. And those are the most cases you will be dealing with in petroleum engineering. Okay? So what we do is, if you imagine this is a plot of that function, okay? One simplest way to approximate would be, okay, take first, this is my interval where I want to integrate between 0 and 1, and decide how many subintervals you'd like. Let's say it's 4. Then, at this point, just take this value of the function right here, evaluate at 0, and then approximate your function as this box here. Okay? Then as this box with value at this point, value at this point, just a box. Okay? So I'm obviously making a mistake here. I'm going to overshoot. Okay? I'm going to have some extra area here. But I can employ a computer to make this subinterval smaller and smaller and smaller beyond what I would do by hand. Okay? So there's some error, but as a my plot has shifted a little. Lift this plot a little. Okay? So basically, as I do, these areas and the error that I'm making will get smaller and smaller because I'll be closer to the function itself. Okay? And then basically, if I actually employ the computer to do that, if I take those 4 rectangles, this is my result with 10, with 100, with 1 million. This is 4/3 for all intensive purposes, or rather, if I'm looking at 4 decimal points only. Okay? So I'm going to get closer and closer to the actual result, but this is a numerical way to do that in the case that I actually don't have a value to the an exact solution. Okay? Now back to that question of having data from petroleum engineering. Can you actually make subintervals smaller and smaller and smaller if all you have is measurement every 1 foot? You have to work with what you have, with the resolution you have. But there are ways you could try to clean up your data and fit it with a function. Okay? And we will actually have an entire section called curve fitting, where you will find a function that looks similar to your data. Okay? Again, with some approximation, so you could use that instead of the data itself. That's an option. In both cases, you have to evaluate how big of an error you're making, okay? And then decide what to go with. Okay? So curve fitting will be, again, I call curve fitting making sense of data. Okay? When you kind of, if you have a function that describes the data, you kind of think that you have a sense. And you can then also use that function to make a prediction somewhere else that is close, for instance, for a neighboring well. Okay? So it's useful to fit the data. All right. So again, as I pointed out through these examples, you use computer to be more efficient. Often the way we design methods, yes, sometimes we derive them from theory, but they're basically following common sense. Okay? There is some proof that that common sense works, and it improves as I put more and more computer power to it. Okay? So if you have to do something in terms of millions of calculations, computer will beat you any time of the day. Because it's faster and it has more memory. So essentially we will employ computers And we will need to learn programming, which is basically telling computer in a structured way what to do. Okay? You also have a trace of what you told the computer to do, which is always useful because our memory is short-lived. Okay? And you can go back to it and correct it as you go. Now, some programming, especially if you haven't done any, will cause you some pain. There's this thing called debugging, okay? And finding typos and errors in your computer. And sometimes all you want to do is punch that screen because it's stubborn, okay? Because you thought you told it to do something and it's doing otherwise. When you want to punch the screen, remember punch cards. And think what you would you do if you had to type it on a typewriter, take the box of cards to a computing center in rain, okay? Get the result after an hour if it works, and then figure out what doesn't work and do that process again. And just be grateful for your screen and that you can do this at your own time at your own computer. Okay? So again, it takes a little bit of practice. For me, sort of on a philosophical level, programming is a very good exercise in giving clear instructions. As engineers later on in the field, the success of your team sometimes depends on whether you can give clear instructions or leave clear instructions of what it is that you did or what it is that somebody working with you has to do. Okay? And basically having this algorithm approach of a step-by-step clear instructions is a good way to sort of develop your thinking in that direction. All right. So, with that in mind, we're not going to start with programming immediately, but we will start with a review of linear algebra because that gives us the tools of how to represent data on computer and how to work with it. So think about linear algebra. So again, I posted both of these sets of slides online. I do suggest, even once we start bringing computers to class, or you might have your own tablet, okay, and refer to these notes. You can write notes electronically. I suggest you do it by hand, and there is a research to support me. There's something that happens, some magic. When you're listening and then trying to write down, you're not as quick as you would be when you're typing. And because of that, you're going to summarize the information you hear. That process of summarizing the information you hear is going to help you understand it better. Because you kind of have to understand it a little to write down. Okay? And there is proof in research, there was research done that says that you're going to retain the information better. So I call that brain-hand coordination. It's been there for centuries for people. So there's some magic in there that works better for your learning ultimately. As far as writing things down, I'm already providing you with the notes. So it's not that you have to rush to write everything, or otherwise it's going to be somehow magically lost. So digital content is there if you need it. There's also textbook if you need it to supplement it. I try to focus on material and kind of write down whatever it is that you jot down. You can always supplement it later. But if you like to do things electronically, suit yourself. Okay? You know it yourself the best. All right, so let's do a quick review. So we have done all of the course introductions, and now we will do linear algebra review before we jump into learning fundamentals of MATLAB and programming and how to weed out errors. All of these first 4 lectures are basically giving us the tools to actually solve something, and the second part of the course is actually applying numerical methods to specific problems. Okay, so our motivation for learning linear algebra, and you probably learned it some in differential equation class, and you're wondering what is the connection here. In general, linear algebra operates with vectors and matrices, right? And that's pretty much the way to represent data, okay? And manipulate data. So linear algebra gives this framework of working with data. It also gives the framework to describe mathematical operators, which is basically the way you use it in differential equations. So it's very broad in terms of applications, and that's why every engineer should know something, a little something about linear algebra, as well as every scientist really. So basically we will have linear algebra gives effective tools. Okay. Now we will do some little bit of exercise here. So try to work in pairs and come up with as many different petroleum engineering data that comes in either as a vector, so one-dimensional data, or some sort of matrix multi-dimensional array. It could be either some sort of lab measurement, field measurement, any type of measurement you can come up with. So let's take 1 or 2 minutes, work in pairs, and then we'll report back. Pairs or threes, whatever works, it doesn't matter. Thinking hard? It's really just about naming it. So any measurement is kind of broad, so I just want to now narrow it down to specific examples. Group 1 here, what did you come up with? Still thinking, have you come up with anything? There we go. So we could have pressure, temperature measurements versus depth. Okay? So for every depth, I have a pressure measurement, for instance, bottom hole pressure. Okay? And that's a point. So for every depth, I get a vector of points. Right? How can I extend that into a matrix? Time. So I can have that on day 1, okay, along all of the depths. Then day 2, along all of the depths. Then day 3, and keep going for 30 years. Okay? So if you're actually measuring it at every depth, this is assuming that you're measuring at every depth, okay, at every time. Okay? So you can easily, immediately extend into a matrix. Okay? And versus time, we get so can you add anything to that? Did you come up with anything else?
The land dimensions, like calculating a rectangular land.
So that would be seismic measurement. Okay. So what seismic does, for instance, it's in space. Okay. And seismic has those thumper trucks, okay, that go and produce sound waves, and it also has geophones that are listening for the response back. So depending on your array of geophones, you're going to get at every point where you have a geophone, which could be 2D, okay, you're going to get a response back. So you're going to get a spatial, right, response, and then those responses are interpreted. So it takes basically team of geophysicists to interpret the data for any kind of, so you will see where you have, for instance, fractures or any kind of differences in the way waves propagate. So you could have that either because of a fracture or change of the medium. It could be different rock and so on. Okay? So that's basically how seismic looks like, and those you could also have in time. Okay? So these days, so basically seismic measurements. So this is matrix. Okay. Did you come up with anything else?
We also mentioned seismic measurements, but our other one was flow rate.
Yeah. Flow rate is, again, it could be same. I'm just gonna put this Q as a flow rate. Okay. So that is another. Any others? Next group, did you have anything different? You're kind of narrowing down the others.
We're talking about like production tanks. Like if you have a tank off the site, you can measure like the level of loss.
There we go. So that's definitely something. So in any kind of tank, I can have volume measurement in production tanks in time. So every time point will give me a different vector value.
We were talking about three-dimensional vectors to find like the position of a drill head and a horizontal drilling.
There we go. So that's basically x1 or x, y, z of a drill bit in time. How's that? So basically I'm going to have a 3D matrix because for every time point I'm going to have a different x, y, z. Okay? And I can put that in a matrix. Anything else to add to? So the only measurements, I mean, here basically we're going through logging and what other, so what other measurements in logging do we have? Anybody else? Porosity and permeability. So I'm gonna put that, I'm just write phi and perm, let it be K. Anything else? A quick smarty pants addition would be I could do a lot of these things in the lab on a core. Then I don't have a very long log, okay? But I will have pressure taps. Let's say that I have a core, okay? The minimum I have is pressure at the ends, so that's 2 points. Small vector, still a vector, okay? But I could have pressure taps getting to the core, however many I put in, really, okay? And depending on the length of the core, so I could have 3, 5, 7 measurements along my depth of pressure, for instance, in the lab. So a lot of these things I could have in the lab, depending on my experimental setup. Okay? All right. So overall, this is how data comes with. It's very hard to actually have, let's imagine this room, and let's say that I want a pressure measurement at every point in this room. Okay? That's extremely, it's sort of an array, right, that I would have to have of sensors that is extremely hard to have. And that's actually a value of numerical simulation. Okay? Numerical simulation, however I discretize this room into blocks, and I can refine it depending on the memory of my computer, I will, based on the Navier-Stokes equation, okay, for flow of fluid, I can actually get that value at every tiny spatial point that I can come up with, provided I have enough memory to do so. And the benefit of numerical calculation is often in being able to refine the results that you otherwise wouldn't be able to measure. Never ever trust anybody who says, oh yeah, we can just drop the measurements and we don't need to ever do them. All I can do is simulation. Simulation has to be grounded in measurements. Measurement provides the boundary values for my simulation, but they often refine that results and enable you to understand what's going on. Okay? So you need kind of both, and you kind of have to often dance between both. Okay, so these are some great examples. So basically, what we will go and do now It's kind of very dry in the sense that we will do it in an abstract sense on numbers that are sort of generic and don't mean much, but they're easy to calculate with just to get some practice. But really think about the matrices that I just mentioned, okay? And that you need to find a way how to work with that data efficiently, okay? And define methods. So basically we'll learn how to add, subtract, and do basic transformations of vectors and matrices, and also transpose matrices, recognize some sort of linear combinations of them, define different types of products, and figure out if two vectors are orthogonal. And we will figure out what norms for these vectors are in order to be able to compare them, because that's often an engineering tool, basic engineering tool, is comparing two things and making a decision accordingly. Okay? And if you want to look at the reading, we're actually looking at the chapter 8 in the textbook, Matrix Algebra Overview. Okay? So vector, formally, is an ordered set of numbers, and they could be real or complex. And I can either look at them as a column or as a row. As far as data is concerned, data has no preference. Okay? You will have to decide how you are entering values. Formally, okay, math or linear algebra does care what is a row and what is a column. Okay? What is a column and what is a row. Okay? Now, so we will denote scalars as lowercase Greek letters, alpha, beta, gamma, and so forth. Vectors as just like lowercase Roman letters, u, v, x, y, b, and so forth. And matrix as uppercase Roman, just to kind of visually differentiate them all. Though again, vectors themselves don't care how you call them, but naming is important to be able to quickly make sense of how you write things down. And in this case, n will be formalization, or m, of length of my vector, okay? So yes, I can have 2,000 or 3,000 or 7,000 values. When I'm writing a method or an algorithm, I should write it in a general case, so I can change that, and if I'm writing a program as well, so that I can change that m or n, the length, at will. And that's the benefit of programming it. Okay? So if I had two vectors, how would you take a piece of paper and quickly add these two? So what is the result? 1, 2, and 5. So even if you didn't have linear algebra intuitively, you would go to the first position in both, add them up, second position in both, add them up, third position in both, add them up, and so forth for the entire length of the vector. Okay? I have just formalized basically an intuitive thing. It's easy to be intuitive when you have vectors of 2 or 3 in size. It's less so easy to be intuitive when you have thousands of numbers looking at you. Okay? So basically I have just formalized it as an algorithm. If you write it down, basically that's how you would design an algorithm. So basically any addition and subtraction will involve sort of corresponding positions, so you will avoid mixing and matching. You're not going to go 0 plus 1 here, or 1 plus 5. Okay? For obvious reasons, we need rules. Okay? Now if I wanted to multiply by scalar one of these vectors, okay, a simple way, so let's say 2 times 210, okay, then I will just go and multiply with 2 every of those positions. Again, a relatively simple and intuitive rule. Okay? And if I wanted to do a transpose, generally, transpose of any matrix, so vector is actually a matrix, just with a simple number of columns or rows. And what transposition does, it just flips the order. Whatever was a row becomes a column, whatever was a column becomes a row. So a vector transpose would from 2, 1, 0 column vector create a row vector 2, 1, 0 with the same elements. Okay. So all of those can be formalized into so-called linear combination. And linear combination says, okay, I can have alpha scalar times a vector u plus beta scalar times a vector v is equal to my new vector w. So I will multiply by alpha every element of vector u and add it to, oh, this should be beta times v. Okay. And that is my resulting vector. Again, intuitive, but it needs to be formalized. This is used where? What is the importance of things being expressed as linear combination? There's some sort of a notion of dimensionality of space. Space has a dimension that is equal to the largest number of independent vectors, vectors that cannot be expressed as a linear combination of others. So if I have a three-dimensional space, okay, I have three vectors. We refer to them as a base, 1, 0, 0, 0, 1, 0, 0, 0, 1. And every other vector is a linear combination of those three. Okay? So when I go to 2, 1, 0, my vector from the previous page, okay, it's 2 times 1, 0, 0, plus 1 times 0, 1, 0, plus 0 times 0, 0, 0, 0, 0, 1. Okay? So I'm expressing it as a linear combination of three base vectors. And I cannot find 4 vectors that are linearly independent in three-dimensional space. So it's not something you would immediately see from this definition, but it's something that you're actually using all the time. Whether something is 2-dimensional or 3-dimensional is kind of very important, especially when you're dealing with data. Okay. So just again, it looks dry, it's formal, but there's a lot of application for it. All right, so let's do a little practice. Take a piece of paper, do these things on your own first. Not all of them are possible. What did we do for the first one? Yes. So it's 2 plus 3 times minus 1. In the first position, this gives me -1. And 1 plus 3 times 1 in the second position, then gives me 4. How about the second one?
I don't think that's possible.
It's not possible. Technically, I have 2 different objects and I cannot add them together formally. You will see in MATLAB will be smarty pants, and it will actually add 3 to both of those positions. It shortens writing of programs. That's their motivation to do it. But formally here by hand, it's not possible because I have different. One of them is a vector of dimension 2 by 1, and the other one is 1 by 1 or scale. Okay. Third one, can do that one either, again, formally, I would be able to do because I have equal number of, the length is the same in both of these vectors, but one of them is a column vector, the other one is a row vector, and therefore I cannot do this formulation, and MATLAB will complain here. It will not let you do it. Okay? All right. I have only 1 minute left, so I will avoid defining inner product. We will continue next time.